The topic for today's lecture is context-sensitive grammars. So, what are context-sensitive grammars? So, before we discuss what are context-sensitive grammars, let us recollect the classes of grammars that we have discussed till now. We know that a grammar G is defined as a quadruple VTSP, where V a finite set of variables. Variables are also called non-terminal. And capital T is the finite set of terminals, or the alphabet set for the language is called terminals. And capital S is a variable called the start symbol of the grammar. And these three are same for all classes of grammars. And finally, capital P, the finite set of productions or rewrite rules. And the classes of languages differ in the structure of productions they use. Let us recollect the classes of grammars that we discussed. The first is regular or type 3. Regular grammars are also called type 3 grammars in Chomsky hierarchy. And you know that the family of languages represented by the class of regular grammar is regular languages. And if you recall, the structure of a production in a regular grammar is like this. A variable in the LHS and in the RHS, a terminal string followed by a variable. Without loss of generality, you can assume that a regular grammar is a right linear grammar. Not that the terminal string could be epsilon. So that's the right linear grammar, and that's the production. So RHS is a terminal string followed by a variable. And the next class of grammars that we learned is context-free grammars, also called type 2 grammar. And we know that the class of language represented by them is context-free language. And if you remember, in a context-free grammar, the productions are of this kind, where the LHS is a variable and the RHS could be any string of variables and terminals. So, when compared to regular grammars, and here the RHS could be any string. Not that in a regular grammar, for a production, the RHS must be a terminal string followed by a variable. And these are the two classes of grammars that we have learned till now. And there are two more classes of grammars in Chomsky hierarchy, and they are type 1 or context-sensitive grammars and type 0 or unrestricted grammars. This name tells you that the next class of grammars are also going to be restricted kind. And today we are going to discuss about context-sensitive grammars and the family of languages represented by them. And before we discuss about context-sensitive grammars, let us try to answer this question. Are there languages which are non-context free? So, what is your answer? The answer is yes. We learned about few non-context free languages. For example, A to the power n, B to the power n, C to the power n is proved to be a non-context free language, and hence the answer is yes. And in fact, there are infinitely many non-context free languages. Examples are there. Infinitely many languages are there. Let us consider two examples. The first one is this language which we have proved as non-context free. Here is another example. Set of all strings over ABC such that the number of A's, B's and C's are same in any string in the language. This can again be proved to be a non-context free language. Now an interesting question is there a class of grammar to generate these languages? Like we have the class of regular grammar for regular languages, the class of context-free grammar for context-free languages. So what kind of language family is going to represent these kind of languages, and what class of grammar is going to generate them? The answer is yes, there exists a class of grammars, namely context-sensitive grammars. And context-sensitive grammar is proposed by Noam Chomsky in 1959. And they are known to be more powerful than context-free grammars. They are very useful to describe the syntax of a natural language where the suitability of a word in a sentence may depend on the context. You know that in a natural language, the use of a word depends on the context of the sentence in which that word is used. You know that you have number of words with the same or similar meaning, and you may have to select the most suitable word in a sentence depending on the context in which it has to be used. And for that, the context-sensitive grammar is a natural choice to define the syntax of such a natural language. Anyway, in this course, we are not going to discuss the application of context-sensitive grammar in natural language theory. I just mentioned an application, that's it. If you are interested in, please refer to the literature and see how effective these grammars are in defining the syntax of a natural language. So with this small introduction to the history of context-sensitive grammars, let us try to understand what are context-sensitive grammars by using an illustrative example. So here is the grammar with 4 productions, and note that here these 2 productions are not following the structure of either the context-free grammar or a regular grammar, because the LHS here is not a single variable. Here it is a terminal followed by variable, and here again. So this grammar is neither context-free nor regular. To see what language is represented, try to derive some strings in this grammar. As you know, you begin with the start simple. If you apply the the second production, you can derive, you can replace capital S with small abc, and thus you are deriving ABC. Try another derivation. You start with the start simple. This time apply production number 1. So capital S is replaced with ASBC, and here I am going to replace this capital S by using production number 2. So capital S is getting replaced with small abc. Not that the other simples are not getting changed. And here I am going to replace this CB by applying the third production. So CB is getting replaced with BC. And finally, in this string, I am replacing small b capital B by applying the last production with a small bb, and thus I derive A square, B square, C square. Now try deriving one more string before we generalize and see what the language is. And applying production number 1, I'll get this. Then in this string, I'm applying production number 1 again. So I'll replace this capital S with ASBC. Not that the other string, other symbols are retained as such. And here, now I am going to replace this capital S by applying the second production. So it's getting replaced with small abc. And what do I do here? I'm going to apply production number 3 to replace this small c capital B with capital B small c. Again apply the same production to replace this CB with BC. And then here again the same production to replace this small c capital B with the capital B small c. And note that now I have moved all the small c's to the right side using the third production. B will ripple through the string and get accumulated in the middle. And now I am going to apply the last production to replace small b capital B with a small bb. Again one more times the same production to replace this small b capital B with small bb, and thus I am deriving a cube, b cube, c cube. Now you know what language this grammar is representing. Before jumping into conclusion, let us try to generalize. Capital S is the start symbol, and here if you apply the first production n number of times, n is greater than or equal to 0, what you are deriving? A raised to n, S followed by BC raised to n. It's very easy to verify it. A to the n times if you apply a to the power n, capital S, BC to the power n is what you are going to get. And here if I apply production number 2 for capital S, this capital S is going to be replaced with small abc. And when I am writing it, A is taken along with a to the power n, so I am writing it as a to the power n plus 1. A to the power n followed by abc, that A is taken here. And that's what I am getting. And now I am going to rewrite this by expanding this capital B small c raised to n. How can I write it? A raised to n plus 1 BC followed by BC n times. Now you know that you can apply the third production to move all the small c's to the right side. How many are there? C is here, then n more c's. So what you are getting is this c followed by n more c's, and all the capital B's n numbers are there. It's getting moved to the middle. And now you know that you can apply the last production to replace all the capital B's with small b's. In fact, you are replacing small b, capital B with bb, but you will get this. It to the power n plus 1, small b, then again small b n times is b to the power n plus 1, followed by c to the power n is nothing but c to the power n plus 1. And thus you are deriving the language a to the power n, b to the power n, c to the power n, where n is greater than or equal to 1. And later you can see how will you make it for n greater than or equal to 0. So with this, now is the time for us to formally define what a context sensitive grammar is. It's a quadruple where you know V is the finite set of variables or non-terminals, capital T the finite set of terminals or input alphabet set, and capital S is a variable called the start symbol. These three are fixed for all classes of grammars. And finally here, see what is the finite set of productions or rewrite rules. The only difference is in the structure of a rewrite rule. And what is it? It's of the form alpha going to beta. The LHS could be alpha and RHS can be beta. And what is alpha and beta? Both alpha and beta are non-empty string of variables and terminals. Non-empty means plus. You cannot have epsilon as either alpha or beta, that is disallowed. Other than epsilon, it could be any string of variables and terminals. So that is why you can have a string of length 2 in the LHS, that is allowed. Any number of simples can be there, 0, 1 or more simples can be there in the LHS and RHS. And other than this condition, one more condition, and that's this. The length of the LHS is less than or equal to the length of the RHS. This is another property. And because of this, you know that if you apply a production in a string, the length of the string cannot be reduced. It is as high as the current string, because the RHS of every production, the length of the RHS of every production is going to be as high as the length of the LHS of that production. And hence the grammar is also known as non-contracting grammar or non-decreasing grammar, because you cannot decrease the length of a string by applying a production in the derivation process. So in that respect, it's known as a non-contracting grammar. And as a special case, the star simple is allowed to have the epsilon production, provided in such a case the star simple does not appear in the RHS of any production. If the star simple is not appearing in the RHS of any production, then you are allowed to have the epsilon production. And you can utilize this in the previous grammar to rewrite it to generate the language a to the power n, b to the power n, c to the power n, where n is greater than or equal to 0. So that's the context sensitive grammar. Now, an arbitrary context sensitive grammar can be converted into a normal form where all the productions are of this kind. What is it? All the productions are of the kind alpha a beta going to alpha gamma beta. So actually what you can replace is capital A with gamma. But in a derivation, the variable capital A can be replaced with gamma, provided A appears in the context where A follows alpha and A is followed by beta. Only in that context you can apply this production. So you are actually replacing the simple capital A with gamma. What is gamma? Gamma can be a non-empty string of variables and terminals. So basically you are replacing capital A with gamma. But to replace capital A, the capital A must be preceded with alpha and must be followed by beta. Only in that context you can apply it. So given an arbitrary context sensitive grammar, you can convert it into this kind of a normal form. And that is why the grammar is named context sensitive grammar. It depends on the context. Then the application of the production depends on the context. So that's the context sensitive grammar. And now let us define what is a context sensitive language. A language capital L is said to be context sensitive if there exists a context sensitive grammar generating the language. For example, a to the power n, b to the power n, c to the power n, where n is greater than or equal to 1 is a context sensitive language, because we have a context sensitive grammar generating it. So with this, we are finishing this lecture and discussion on context sensitive grammars, and I am giving you 2 practice questions as assignment. So the first question, I am giving you a grammar. It's very easy to observe that this is a context sensitive grammar, And what you are asked to do is find the language represented by this grammar. Try deriving strings and later generalize. And find the language and also argue that your answer is correct. So another practice question is, given this language, which is known to be a non-context free language, you prove that this is a context sensitive language. How can you prove? You try to find a context sensitive grammar generating this language. So today we learned about context sensitive grammars, where a production is of the form alpha going to beta, where both alpha and beta can be non-empty strings of variables and terminals, such that the length of the string alpha is less than or equal to the length of the string beta. And an arbitrary context sensitive grammar can be converted into a normal form where all productions are of the form alpha a beta going to alpha gamma beta. That is, in fact, in a production or in a derivation, you can replace the variable capital A with gamma, provided the capital A is preceded with alpha and is followed by beta. So only in such a context you can apply a production in context-free grammar, context sensitive grammar, and that is why this class of grammar is named context sensitive grammar. And we define a context sensitive language as a language represented by a context sensitive grammar. Thank you.